Bonsoir, and thank you very much for hosting me on the 30th birthday of the software. In December 1995, I was working for a object-oriented consultancy that was doing C++ and Smalltalk, and I started fiddling with the Sun Microsystems Java language, which came out and was being pitched for doing applets, running little programs in the browser. And I looked at the language and I thought, this is quite a good language. I think we could use this on the server side. So I pitched to my boss that we should start doing office automation, issue tracking systems and things like that, written in Java on the server side. And he said, there'll never be any money in Java. There'll never be any money in that, which is pretty amazing, seeing it's pretty much the business plan of Atlassian, which is a $4 billion company now. So anyway, I quit. And I went away and wrote an issue tracking system in Java that had an HTTP server at its core, and that HTTP server has grown into the Jetty project and has sustained a small company for 30 years. And we feel we've gone from strength to strength. And so on the 30th birthday, I just thought I'd do a presentation of some of the things that have helped us keep relevant over 30 years. And some of the things that have changed and stuff. So it's a bit of a retrospective and me just rambling around. So I went back and had a look at the Wayback Machine to see when I could first find references to Jetty. And it turns out that Jetty existed before the Wayback Machine did. So the Wayback Machine only started scanning in the late 90s. So this is from January 1998. And you can see that this was my personal services company at the time. We'd already picked the name Jetty, and we had an issue tracker that was running on it. No one liked the issue tracker, but people got quite interested in the HTTP server, and things started, building from there. So, and just to show you how things have changed over 30 years. This is actually 25 years. This is again playing in the Wayback Machine. It was in 2000. I found an article in iX magazine that was rating the Java web servers at the time. So we had Jetty, Jigsaw, Java Web Server, JServe, JRun Pro, and Jetty came out the best. We topped the benchmarks at a massive 200 or so requests a second. Oh, look at that! And that was some achievement back in those days. Oh, I should say that when we started writing HTTP, Java was not that good for networking. It didn't even have a close method on sockets. So we had to basically do a hack to, in HTTP 1.0, you need to close to end a message. So it was pretty raw for networking. So getting that sort of request rate and that was enough to serve most web applications back then. But of course, the web scaled. And here we are 25 years later than that. And this is the benchmark that we run regularly on Jetty. And here we are doing 1 million requests a second thank you, yes. Hooray. And not only is this 1 million requests a second, one of the things I think that's kept the project relevant is we really focus on making realistic benchmarks. So I have a real bugbear about benchmarks where you just throw traffic at it and you see how many requests a second it can do, because that's not realistic and you're not really measuring throughput. More often than not, if the rate you offer requests is a function of how long it takes for the previous response to come back, then when you report, oh, I achieved 20,000 requests a second, you're really measuring latency. So what we do is we offer a fixed amount of traffic. Here we are, you can see that the traffic is pegged at exactly 1 million requests a second. So we offer that throughput, and then what we measure is the latency. And the latency, the reason we measure it is it's really a measure of the quality of service. It's, you can serve a 1 million requests a second, but if they all take 10 seconds to return, it doesn't do you any good. And back in the day, the Tech and Power benchmarks, when people used to hack the benchmark, there were ones they ran the benchmark for 30 seconds, and there was ones that high up in the ranking where the average request time was 15 seconds, which meant all the responses came at the end of the 30 seconds. Anyway, so we measure latency, gives us our quality of service, and here where most of our requests, 99% of them are coming back these are microseconds, not milliseconds. So that's 0.07 of a millisecond is 99% of our requests. And we also look at the long tail. So the 1% is 2 milliseconds. And we're doing this on a server that's 30% idle, because you never really wouldn't want to go into production with a server that's 100% busy. I think 30% idle is a little tight. 40% would be better, but we wanted to hit the big number. So you have to allow us some vanity. And the way we do that is, in order to generate that constant load is actually rather difficult. Being a client is harder than being a HTTP server. So Jetty is both a client and server. So we run 5 load generating machines, and each of them generating 200,000 requests a second. So if you need a high throughput client, Jetty, our project, we've got one of those as well. And we bombard our little server there. Well, nowadays it's 64 cores, where I think the benchmark I showed you was a 2-core machine. So we've got a bit of a scaling of CPU power to help us there as well. And that's how we get that load on there. But the other thing we do is, when we actually measure the latency, we'll just get another machine off the side and run a smaller number of requests over it to make sure that its client's not being stressed. And we measure the latency both on the server and at that client. And so it comes back to the quality of the service that you're achieving. And latency is a very bad, high latency is very bad for quality of service. So we want to see fast responses, and we want to see short tails and reliable same results over a long time. So that's how we achieve that. Anyway, so enough on the benchmarks. That shows you how much has changed. So that's 4 orders of magnitude in 20 years, 25 years. Some of that being the machines, but a lot of that's being the software. So back to the question of how do we keep Jetty relevant? Because as a HTTP server with a server API on top, we're kind of sandwiched between the RFCs below us, which say how we run the protocols, and we have the servlet specification above us, which controls our API to our users, and then there's a million different frameworks. So we're not really that exposed to a lot of software developers. So we have to make sure that that our strengths speak for themselves in order for people to say, oh well, an HTTP server is not commodity. I mean, I've been doing this for 30 years, and every year I say, well, next year no one's going to care what HTTP server they're running, because it's just going to be a commodity. You're just going to get them. And I guess for a large number of applications, HTTP is commodity. But luckily for us, our business, there's still some who really care about hitting those high numbers or hitting the flexibility that we can give. So we're not commodity just yet. And so let's go through some of the ways we get there. So one of the things we've done over the 30 years is maintain a vision of how we want the software to work. And that's not just from a programming point, it's what it does. This is a quote from our website in 1998. Jetty intends to be the server inside the application rather than the application inside the server. And what I mean by that is that over the 30 years, the way we deploy software, the way we write software has changed greatly. The configuration style we use, dependency injections or configuration files, the logs that we use to debug the thing, everything's changed. And if we tried to be the application server and say, this is the way of doing it, we'd have to maintain a set of users that want to do it our way for all those 30 years. And we'd have to be right for 30 years and pick every change of fashion. And that's not what we were trying to do. What we first do is we make good components. We make good HTTP components for a client. We make a good HTTP component as a server. We make good implementations of the API that can be put together in many different ways. Yes, they can be put together as an application server, but they can also be embedded in your application or embedded in your platform. And this way, our community of users brings us along the current best practices and gets us, uses us within their systems. And so we have been brought along with the tide of how they change. So some examples of that is ActiveMQ started using us as a transport for their messaging. Presto does the same thing, which is the database behind Facebook. And they just use us we're embedded in there as a transport. And they're using our client and our server. What they're interested in is very, very high throughput. They're the ones that are pushing us to those million requests a second. Then we might have someone like Spring Boot, where you can have Jetty running inside Spring Boot, and the users there are writing their applications and Spring and other things on top of that, and they just want a good HTTP implementation. And so we're an embedded HTTP implementation for Spring Boot, and we get the way Spring evolves and the way they develop applications, and we just provide them a very high quality HTTP layer in there. Then we've had people like Google App Engine, who use us as a servlet container. So Google picked us up because they wanted the Servlet API to provide that on their cloud platform, but they wanted to replace a lot of our components. So they don't use our session management. They put their own session management in there. They put their own authentication layer in there. But we used Jetty primarily initially as a servlet container and not with the HTTP layer. And now they're using a bit of both. And so again, that's because we're flexible components when we can be put together as an application server, but our primary focus is making good quality components that can be used in different sort of ways. And then finally, we have clients like or users like Salesforce who do use us as an application container. They use the way we assemble the software as an EE style application server, and they deploy their application in it. So by being flexible in the way we get used, we had the flexibility to be used in lots of situations, and we've been able to have lots of different users to give us influences to how to develop the software. Okay, another vision that we've had, and you saw a touch on that before, is speed is king. Is like it's whatever we do, we always come back to the server has to be fast. If we're not fast, then we just don't rate. We would become a commodity. We would disappear. So I've got a little war story of the sort of things we have to do to stay fast. Back in 2012, we were moving from Jetty 8 to Jetty 9. And so what we were doing was we were breaking down all little components and micro benchmarking them in the bad style of benchmark I don't like, of running to see how fast they can go. But that's actually quite good for micro benchmarks. And we improved a lot of our components. So here we can see our HTTP parser, it improved by about 5%. And our IO level improved, well, probably that's noise. It didn't get worse. So we went through all our components and made them better. So we had great expectations that Jetty 9 was going to be a little faster than Jetty 8. So we were a little bit disappointed when we put it all together. Oops. And Jetty 9 milestone was about 20% slower than Jetty 8. I was like, whoa, what's happening here? You know, how can we get faster components, put them together, and end up with a slower whole? And basically, we spent a lot of time analyzing it. And what it turned out to be is that inside a server, you have a lot of produce-consume models where you produce tasks that can get consumed. And typically we were, because we had to, the consuming of a task like processing a request could go to an application that might block. We'd have to use a different thread quite often to consume those tasks. And so we had this sort of model where you'd have one thread reading requests, giving them off to a thread pool to be executed. And in the change from Jetty 8 to Jetty 9, we moved the point in the reading, parsing, handling that we did that dispatch to a different thread. And what happened, if we see here in this little diagram here, where we have 5 tasks found by thread 1, we were dispatching it to a different thread. And on a modern machine with lots of cores, that when you go to a different thread, the chances are nowadays 1 in 64 that you could be on a different core. If you're on a different core, you can get a different cache. And so if you've just gone and parsed a request on one core, and that core's cache is full of all the fields of that request, and then you dispatch to a different core, you get cache misses as you start to execute that request. And it turned out the reason of the slowdown that we were seeing in Jetty 9 was that our instructions were running slowly because of the cache misses that we were getting looking at those requests that we just parsed. So we came up with a different sort of scheduling algorithm, which we I initially called eat what you kill, but I was told that wasn't politically correct. So I was beaten up by my colleagues, and we now call it execute, produce, consume. But for tonight, let's call it eat what you kill. Where if you eat what you kill means that if you produce a task, then you should consume it. Because if you produce the task, your cache is hot. It's full of all the data from that task. So you're the best core to do that. And in Java, it's, you know, there's no way of pinning cores, but by running in the same thread, you're pretty sure you're going to be in the same core. So what we do with execute, produce, consume, eat what you kill, is whenever we produce a task, if there is another thread available to take over production, then we consume it ourselves. We only dispatch it to a thread pool, which might end up on a queue or something, if there's no thread available to take over the production. We have to ensure that there's another thread to take over the production, because if you don't produce, you can stall. And if you're not reading that next request, especially with HTTP2, where the flow control was done in messages, if you don't produce that next packet coming in that does the flow control, you'll deadlock. So you have to always produce. So anyway, with this sort of scheduling change, which we didn't just put in the bad spot, we'd put in between 8 and 9, we put it all through the architecture. So it's from the parsing all the way up into HTTP2. So I think sometimes we chain 3 of these models together. We got a significant improvement. So here's Jetty 9 coming out. I'd say that's probably 15 to 20% faster than Jetty 8 eventually when we released. And so that was us making speed is king. We'd improved the software, we'd fixed lots of bugs, but we didn't release Jetty 9 until we knew it was significantly faster. And it was a massive effort to find out why. And it was a bit of a re-engineering to make sure it was faster. And that was the decision that worked then for those JVMs, and something that we have to keep reviewing and revisiting constantly. So, okay. So yeah, and so that optimization we did there was a bit of mechanical sympathy. And so that's one of the things we definitely always look at when we're writing a Jetty, is mechanical sympathy means you have to be very much aware of the hardware that you're running on while you're writing the software. I know Java's a virtual machine, but if you're not understanding what you're running on, you're not going to be running as the best those machines can go. So we spent a lot of time picking our data structures and our locking structures to try and make sure we've got the most mechanically sympathetic choices. If we can't find one in the JVM, we do write our own. We're very reluctant to write our own. Writing good, concurrent, scalable data structures is amazingly hard, and we've written quite a few that we thought were wonderful and brilliant and micro-benchmarked perfectly and ran for 2 or 3 years, only for a horrible bug to be discovered down the line. But we've got a core of quite good ones here. Ray try is what we use for, instead of a hash map, for looking at matching strings as they come off the wire, looking for your method get and that sort of stuff. And it's very much about memory locality, making sure that as you're looking through a tree, you don't go through object to object to object, which might be different in locations in memory, and do cache line misses. It's all in the same array. The G, the E, the T of get will probably be next to each other in that array, and therefore will be found nice and quickly. But then when we have some blocking array queue, which is where our data structure we use for pulling jobs off queues, we have to go the other way around, where we have to be cache row aware that if you're modifying some things, you don't want them to be in the same cache line as things that you're reading, because you'll flush it when you modify, and the reader, which is more frequent, will be affected. So again, that's a data structure that if you look at the code, actually queries to work out how big the cache line is, and make sure that the head and the tail pointers are separated. We have a concurrent pool, which we use for pooling connections and pooling buffers, and we don't actually use it for pulling threads, I don't think. And it's all about reducing lock contention. Actually, I don't even know it's well, is lock-free, but contention on the lock-free, even the CAS things, you want to be a lower contention. So it uses an array of them and spans out the requests over multiples of them. So it's lock-free contention, yes. So date cache, we do temporal optimization. If you're doing 1 million requests a second, they all want a date field in there saying what the date was and its resolution of 1 second. Then you don't really want to format that date 1 million times. You just format it once and use it 1 million times. So we'll do temporal optimizations like that. Our queued thread pool, we spent a lot of time looking at how it hands off tasks, how long it takes to get the thread back around to get the next task. And then our adaptive execution strategy is doing the eat what you kill. It's very hot cache aware, but now it has more different strategies it can pick from, and we try a lot of heuristics to make sure it picks the right strategy. And we've added in virtual thread support into that as well. So we can move with the times, and we'll see a bit more about why we might need that. So if we want to look at what a flame graph looks like of a server that's handling 1 million requests a second, this is our flame graph. You guys can't read that, which is good because you'd probably find a few things in there I couldn't explain, but I'll do some highlights. So over here, that's our polling, where we're looking for connections that have active requests. And it's good, the red bits here are system calls. So once you get into a system call, there's not much else we can optimize. So it's good to see that in a busy server, we're spending a lot of time in the red. We're spending the time looking for requests. And then if we find a request, we have to schedule it. So that's the cost of our execution strategy there, sitting on the right. The red at the top of that is the locking involved with that execution strategy. Everything has a cost. Then that's us reading the data in from the requests. So again, it's like if you're going to be a server and you're reading requests, you have to read that data. So the bigger percentage of the overall graph, the red is there, that's good. So we're reading our requests. Probably could consider the polling and the reading together of how we get our requests in. Parsing is a big effort of HTTP. So all those little peaks there are basically our parser of working out all the different bits of the requests. And when we're sending our requests, we're sending realistic requests that have a lot of fields in them that change, not like a lot of benchmarks. It'll just send one field or one request and constantly always the same. So we do actually have to parse it, and we do pay attention to it. But then when we generate our response, I think it's that little tiny shoulder there. Generating we can do very quickly. We do a lot of pre-generation of fields, common fields and things like that. And the nice big one is writing. So as a server, our job is to write data out onto the network. So that's a big red plateau. That's good for us. The more red plateau of writing means the more we're doing our job. The more data is getting out in the network, and the more time we're spending not doing other things. And then the final big red plateau down, stats. All this here is because we collect stats while we run our benchmarks. It takes a lot of effort to gather stats. So if we didn't gather the stats, we'd probably have a more meaningful application in there other than Echo. So let's call stats the application that we're running. And then finally, waiting. This here is the server's only is 30% idle. So we actually have threads sitting in the thread pool, not doing anything, just kicking their heels, waiting to do something. And that's those threads waiting there. So this server could handle more requests. It could handle a burst of over 1 million. And that tower there would disappear and be more work over there. But I highly recommend you wouldn't deploy something in production that didn't have a big fat tower here of threads ready to handle a nice peak load. Okay. My final vision that we've had throughout the 30 years of the project is be an innovator, but if you can't innovate, be an early adopter. You want to be on the front wave of new developments, or at least near it. And we can't always be the innovator, but adopting early has kept us relevant. It might not necessarily be good business for us. A lot of the things we've done don't generate any revenue, but they have kept us there, and you never know what comes from those efforts. So this is a pretty pathetic slide, or I'm just listing a few things where we either innovated or early adopted. So we've gone through the whole HP 0.9, HP 1, the 3 different versions of HP 1.1. I don't know why there's 3 different versions of it, but there were. Speedy came along as the idea of how to improve HTTP, and we were very much part of that effort of being very early to implement that and feed back into that design of that protocol. We had to do things like modify the JVM so we could do the next protocol negotiation over SSL, and that put us on the forefront of that area. And so therefore, when HTTP 2 came out, we had a very good HTTP 2 implementation very early on. Did us no good whatsoever. No one used it. It's taken quite a few years before HTTP 2 has made penetration into the data center where we're most likely deployed. And it's only now that we're seeing a lot of HTTP 2 take up. But it's good that we've had years to refine our HTTP 2 development. And then we're seeing, hopefully we're going to see the same pattern with HTTP 3. We've put a bit of effort into getting an early implementation of HTTP 3 out there. No one's using it. Or if they're using it, they're not telling us. We're an open source project, so it's very hard to know that they're not complaining. We're not seeing much uptake. But by being there, we have the experience. So when something turns and people say, oh, HTTP 3 actually is worthwhile, this is really where we want to be, we have that in our project where we have the experience, we know it's there, we can go with the times. The same thing is with the specs. We very much participate in the RFC process when we can. We follow the changes to the HTTP protocol as soon as we get an opportunity to, but we also look at the WAT working group, which is like, for instance, the W, oh no, I won't be rude, which is a living document specification that the browsers use. I don't know how you can actually say a living document is a specification, but it's a documents that record whatever the browsers have decided to interpret the RFCs as at the time. So we have to be very proactive to follow what the browsers do because they are our direct users. I won't talk through these. I've got some better slides on those. Okay, yes, we had a big move in the EE world of moving from JavaX to the Jakarta namespace. Again, we were early adopters of making a version of the server that's available to do that. But the other thing we've done with Jetty 12 is we've made it possible to run both at the same time on the same server. And this suits customers that have large numbers of web apps who are migrating one at a time. And they can put a JavaX and a Jakarta one on the same server. They can even do cross-context dispatch between them, which cooks your head sometimes, but it works. Although there's not that many, that's a deployment mode which is less out of favor now of having one server and multiple web apps running on it. But the fact that we have the one server that can run both EE8, EE9, EE10, now EE11 applications means we have the one code base, the one configuration, the one set of bugs, one set of features that you can deploy all your applications on, your legacy ones and your newer ones. So that was quite a good feature that I think we're the only ones who are currently doing it, and it seems very popular among our users. So we definitely have people who are using Jetty on all those different environments, JavaX through the various Jakarta ones. We've spent a lot of time in authentication, doing OpenID, Spinigo, Ethereum. No one uses them, but we're there ready. If there's a good usage for them, that'll come back to us. They're there. So same thing with containers. We haven't any one container. We've made sure however people wish to assemble their applications, we will help them out. If it's using Spring to do dependency injection, you can put Jetty together that way. OSGI, all our components are OSGI, JPMS, and we support CDI in both the CDI inside the web app and in CDI to configure the web app nodes. So again, this is the flexibility of don't pick any winners and make sure you're involved in adopting technologies, because you don't know where the next wave is going to come from, or if you do, you're really smart. And again, so currently where we're at the moment is Loom came along, which is virtual threads. I don't know if anyone's read any of my blogs. I'm virtual thread skeptic, but it certainly is there a lot of efforts happening in virtual threads. So even though I think it will ultimately be a massive failure, we are supporting virtual threads and experimenting with them. And I've got my rest of my slides give a little bit of a look at the alternatives of those. So with all those early adoptions and stuff, it's really key to listen to your users. Is like we've listened to our users even when they're doing what we think is stupid things, and it's led most of our innovations over the 30 years. So back in, I think it was 2005, ActiveMQ, we just sort of got servlets out there and we were concentrating on making them fast. And then ActiveMQ started doing sleeps inside of their servlets, waiting. And so they could push out messages. So they were doing transport in two directions. They were basically doing very early comet type stuff. And of course, that just filled up their thread pools. And so they said, oh, can we have a way of not, of sort of suspending a request and then resuming it? And so we came up with continuations for them, which, if we look at the code for that, is basically when you get a request in, you do a little bit of processing. Do I have a result ready? No, I will create a continuation. I shall suspend it until something asynchronously provides me the information I need. Then I'll resume, and on I go. And the suspend and resume was done in this case basically by unwinding the stack all the way out, and we could reconstruct the stack by rerunning the request. So anything that was associated with the request would come in with the request, we'd go into the context again, we'd find the servlet again, we'd turn up there on the resume with the same stack that we'd recreated, and then we could finally write the output there. And so this was a very early attempt of allowing asynchronous waiting without having the users to write a lot of asynchronous code. And that's basically the same problem that we've been trying to fix for 20 years. So virtual threads is still addressing this problem of how do I not have to write asynchronous code, but I want to save my context and come back here again. So we'll see somehow that's changed over time. So anyway, from continuations, we eventually developed async servlets, which went into the spec. That spun off into Comet D, which is a push framework that we support. And also the servlet started adopting async IO, which we're heavily involved in actually doing the APIs for allowing users to do async IO. And so this is all about making our servers scalable so they can do a lot more, approaching the 1 million requests a second. And then we listen to our users. WebSockets comes out of the same sort of effort. We listen to our users, and around 2010, they go, oh, we don't really need, 100,000 requests a second per server. We're going to go into the cloud. We're going to use lots of different servers, and each server can do 100 requests a second. And if we get a burst of traffic, we'll just spin up another server. That's what we want to do. We don't care about the raw request rate at any given server. So we had to change what we thought was important. So we developed something called Quick Start, which was, if we're going to be in the cloud and you want to spin up a new server, it has to be done quickly. So at this time, I think, some EE applications were taking, 15, 30 seconds to go scan all the configurations, scan all the jars, find all the annotations, and get themselves up and running. Well, that's not good enough to spin up a new instance. So we added a feature of Quick Start, which can spin up a new server instance in about 100 milliseconds. You don't need a picture of this, Ludo. You made us do it. So yes, that was, again, following our users to force us to innovate. Okay, so we have Quick Start in there. Then around 2020, we start getting lots of whinges, from the users listening to it out there that async's too hard. We'd spent the last 15 years making it so we could scale asynchronously and give asynchronous APIs to our users. They could suspend servlets, they could do async IO, and It is a way of making things go very fast and to scale really well, but it is hard. We make lots of mistakes, and our users made a lot more. And so that was the feedback: is programmers don't want to write asynchronous code. So we tried reactive. There's an effort out there of people saying, well, let's do reactive APIs. It's a better way of doing asynchronous. And it was sort of okay. But, here we are in 2025, and people are still saying async is still too hard. Don't want to do it. I don't care if it scales. It's too hard. Let's not do it. So virtual threads is being proposed as a solution to, I don't want to have to write asynchronous code. I can have 1 million threads, all, writing blocking codes, 1 million threads. And there is probably some goodness in that, but I am skeptical. Basically 35 years ago, Sun Microsystems tried it with their M times N threading and failed miserably. And I think we're following the same path, but you have to be participating to see what the users want. Their need to avoid asynchronous programming is true. Whether virtual threads is the solution, I don't know. So what's the alternative? Well, what we're currently offering in Jetty is that we write the server is asynchronous, but your application can be blocking. And so we're providing more and more services wrapping around a blocking application that can make it act asynchronous, but the code's still blocking. And the final thing I'm going to show tonight is basically an interaction diagram of how that can work. So if we have an asynchronous server, then as a request comes in, we can start asynchronously seeing, oh, there's some IO, I'll read that, I'll parse that, oh, there's not enough a full request here, I'll threadlessly wait for some more. And that's always been the lower layer of, for the last 15 years. But what we're doing now, we've got something called an eager content handler, which not only does it read it, it starts parsing it. So if it's a form or an XML document or a multi-part, it actually parses it and makes it into your objects asynchronously as it goes without talking to the application. So you can get multiple asynchronous cycles building up until we actually have the full content. So when the full content comes, the eager content handler says to the next handler in the chain, oh, I've got a HTTP form, I've got a multi-part content, I've got an XML document. Why don't you handle it? So the next handler we can put in our chain is what we call our quality of service handler. Whereas, if your application is doing something that can't handle 1 million virtual threads at the same time, let's say it's going to talk to a JDBC database and the JDBC connection pool's got 100 connections into it, then throwing 1 million virtual threads at your 100 connection JDBC data pool is not going to end well. So we need to restrict the number of requests we'd let through to that part of the application. If we know they can only handle 100 simultaneous requests, we'll only let 100 through. And rather than blocking, waiting for a connection from the JDBC data pool, our quality of service handler can asynchronously just let the request return. And we threadlessly wait until sometime later, another request, an unrelated request, finishes and comes out, exits out through the quality of service handler and says, I'm done, I'm finished, I'm not using the database anymore. So now we know that we've got another count that we can use. We can wake up our request again. And finally, after having read all the data, parsed all the content, checked that we've got not too many at once, we finally dispatch to our handler, which is our application, could be a servlet, could be a handler written, that could be written in blocking code. And so that blocking code can now just run ahead, handling those requests with the database it has access to. If we want, we can run in mixed mode. That thread could be a virtual thread, and it could, if it had to talk to a back-end services and it wanted to wait for their responses, then you could use virtual threads for that if there wasn't an asynchronous API. And then finally, it comes time to write the response back. And so what we do is we normally have, our normal response has big buffers, but if you want to have the entire response, you can put a buffered response in there, which will take the entire response. And just lets the response get written into memory and buffers the whole response. Now, you might say, well, that's costing memory. But will any of these solutions cost memory? If you're using virtual threads to not be asynchronous, you're saving stacks. That's memory. So you've got to spend memory if you want to avoid writing asynchronous code. So anyway, we buffer up those writes coming from the handler until it finally says it's success. And then once it says success, we can asynchronously flush that on behalf of the application. So it's then we go back into asynchronous mode. And I think this is where the state of scaling applications is at the moment. We know how to scale servers. We can write servers that do 1 million requests a second. Can we write applications that do 1 million requests a second? Well, some yes, but generally asynchronous is hard. Virtual threads is being looked at as a solution. There's no solution for that JDBC issue with virtual threads. So hopefully this is playing out at the moment. So we'll see where it ends up. Okay, so that's 30 years of Jetty. Just a couple of war stories of how we've tried to keep the server relevant. I have a few T-shirts here. If anyone asks a question, you can get a T-shirt. There you go, bling. I'm bribing engagement. Any questions? Am I just going to throw the T-shirts at you? I'll get a T-shirt cannon. I'll shoot someone. Oh, okay.
No question? Yeah.
Hey, thank you for that. Any war stories about security incidents?
The one war story I like is we were working with E-Trade, and we were doing one of our early things was continuations to do server pushing out things. So you could have little web applications that would have your stock portfolio on the screen, and when the share price changed, we'd push the new share price out. And this was, within E-Trade, they had, traders, and they had God traders up in the high office there. And what they found out was happening was that if everything was over SSL, so you couldn't see the content of the packages, but you could actually see the timing of them going there. And so if you see on the same network as the God traders, and you watch, and they had their portfolio on their webpage, and we were pushing share prices at them, you just record the time that we pushed a packet at them, and then you'd go say, well, what share price has changed? Maybe there was 100 share prices changed that millisecond, and then you just do that statistically, and all of a sudden you find out what's the portfolio that the God trader is looking at, and you can steal his portfolio, which is sensitive information. So that was an amazing thing, that timing is all that's just encryption is not enough. People say, use a VPN so no one knows who you're talking to. Well, you can just see when packet goes into the VPN and comes out the VPN, and statistically, the bad guys can work out who you're talking to. So, and the two amazing things is that it's possible to do, and that people were doing it. And I guess chess.com is another one where chess players they play 5-minute games of chess, and we were doing the timing on the server in the prototype that we built for them. So when the move came in, we said that's the time of the move, and they were saying, oh no, but it took 30 milliseconds to get across the network. That's 30 milliseconds that the user should have on their chess clock. We'll let the client send the time that the move was done, so that we will trust the client sending the timing across. And sure enough, people reverse engineered the protocol. They worked out that they could spoof the timing. So every time they did a move, they would take a few milliseconds off, so their clock was better. So again, amazing that someone worked it out, and that people cared about it so much that they actually did it. So so it's on people. There's so many people out there using the internet, and there's going to be someone who's bored and wants to have a go at breaking something, and some of them are very smart. So yeah. Ooh, what size are you? Medium? Large, okay. Any other questions? Medium. Large. Or do we have another talk?
Yes, thank you for the presentation. Having worked so long on these challenges, because these are really just mostly challenges, I guess some of you have been also contributing to the Java, the GVM. So I've been kind of curious how much of what you learn working of this problem have been actually implemented in the GVM.
Personally, I haven't contributed very much back to the JVM, but Simone has been key on the JVM team. We certainly do maintain dialogues with them. We've found JVM bugs, we've pushed back to them. But to the first part of the question of how do we maintain interest and engagement for 30 years, personally, it's the space is very good, is that the web has grown and gets used for amazing different things. So one week we're chess experts, next we're trading experts. So we get to touch on lots of different things. I think we've had one, I don't know if Jetty's flown in space, but it certainly helped satellites get put into space. So yeah, you get lots of different areas that you can get to work on. So that's kind of cool. All right, so that's, I think that's another, you'll have to be a medium.
Can I get a shirt if I put the Jetty logo in my slides?
Yes, you can. That's a question.
A medium, please.
A medium, there we go.